Hello everyone, in this video we're going to be looking at section 10.3, which is parametric equations and calculus. So remember, now we're looking at parametric equations. So we have an x equation that is a function of our parameter and a y equation that is our function of our parameter. All right, so let's go ahead and talk about subsection 1 here, which is slope and tangent lines. So we start out with the theorem 10.7, the parametric form of the derivative. So if a smooth curve C is given by the equations x equals f of t, right, our x is a function of t, and y equals g of t, right, y is a function of t as well, then the slope of the curve C at xy is dy over dx is equal to the derivative of the y variable, the y equation with respect to t, over top of the derivative of the x equation with respect to t, right? And that's provided that the derivative of x does not equal to 0, right? So again, the idea here is that if I had a regular Cartesian coordinate xy equation, then I know how to find the derivative, right? That was Calc 1. So now the idea is I have, instead of that, I have these two parametric equations. How am I going to find the derivative or an equation for the derivative at any given point? Well, this is how I do it. I take the derivative of the y function over top of the derivative of the x function. Okay, so in order to find dy dx for the curve given by x equals sine t and y equals cosine of t, what am I going to do first? I'm going to find my dy dt and my dx dt, right? So let's find, we'll go dx dt first, right? Dx dt is the derivative of the x function, which is sine of t, so the derivative of sine is cosine of t. And then now we do the derivative of the y function, so dy dt is the derivative of cosine, which is negative sine of t. So now the formula says if I want to find the derivative dy over dx, now notice the different variables in the denominator. I was taking the derivatives with respect to the variable t, so that's why I had t in the denominator. But if I want the derivative of the curve, remember the curve is plotted in the xy coordinate system, right? So I want the derivative function to be the derivative of y with respect to x. And this will again be a function of t that I can plug the parameter in to find the derivative at any given point, right? So here I do my y, which is negative sine of t, over top of my derivative of x, which is cosine of t. We know that sine over cosine is tangent, so this ends up being negative tangent of t, right? That is my derivative function that I can plug my parameter t into. Okay, so since dy over dx, that derivative function is a function of t, we can use theorem 10.7 repeatedly to find higher order derivatives, right? And so this is important because notice if I want to take, say, the second derivative, one would think I would take, okay, let's do the second derivative of y over the second derivative of x, right? That seems logical, but that's not actually what happens here. I want to either take the derivative of the derivative, or, which that doesn't make sense because in this case we have a function of t, so the way we're going to do it actually is going to be this formula here. And so basically what we want to do is take the derivative of the derivative over top of the derivative of x, right? So that's how that one works. We take the derivative of the derivative, so in other words that's why it's the second derivative, but we put it over top of the x derivative. Okay, so for the curve given by x equals the square root of t and y equals 1/4 t squared minus 4, we want to find the slope and concavity at the point 2, 3. Right? So first and foremost, let's go ahead and find the first derivative. Right? So our first derivative, again, how do we find that? Well, we first find dx dt, right, the derivative of x, and that's going to be 1/2 t to the negative 1/2. And then I want to find the derivative of dy, so dy dt is going to be, if I multiply this out, it would be 1/4 t squared minus 1. So I would bring the 2 down, so I end up getting 1/2 t. Right? So that means that dy over dx, which by definition is dy over dt over dx over dt, So dy over dt is 1/2 t. Dx over dt is 1/2 t to the negative 1/2. And now we're going to be able to simplify some, right? I have 1/2 t. Now instead of dividing by 1/2, I'm going to multiply by 2. And then instead of that t to the negative 1/2, remember I can pull it up into the numerator by making it positive. So t to the positive 1/2. So now my 2's cancel out, and I'm left with t to the 3/2 power, right? Because I add their exponents. Okay, so now I find my second derivative, right? And again, to find my second derivative, what do? I first find the derivative of my derivative with respect to t, right? So in other words, d dt, which means the derivative with respect to t of what I just found, dy over dx. So in other words, the derivative with respect to t of t to the 3/2, which is 3/2 t to the 1/2, right? But that's not how I found my second derivative. My second derivative is d squared y over dx squared is equal to the derivative of my derivative, dy over dx, over top of the derivative of x, right, or dx dt. So it ends up being 3/2 t to the 1/2 divided by the derivative of x, which is 1/2 t to the negative 1/2. Right, so I end up getting here 3/2 t to the 1/2 times, again, instead of dividing by 1/2, I multiply by 2, and instead of dividing by negative 1 t to the 1, or 1, try that again. Instead of dividing by t to the negative 1/2, I multiply by t to the 1/2. So I end up getting just 3t. Right? So I know right here I have my function for my derivative, and right here I have my function for my second derivative. So now it says, let's answer the question. Find the slope and the concavity at the point 2, 3. Well, how does that help me? I have the point 2, 3, but then those are x and y values, and these are in terms of t. So what I need to do now is find the t that corresponds to that point 2, 3. So I need to find the t that corresponds to the point 2, 3. Right? So let's look at my x and y equations, right? My x equation says x equals the square root of t, right? So what t value do I need to put in there to get x equals to 2? T equals 4 would give me x equals to 2. And you notice that if I looked at this guy, which is 1/4 t squared minus 4, it should also work for this, right? If I plug t equals 4, I should get 3. Notice I get 4 squared is 16 minus 4 is going to give me 12 divided by 4 gives me 3, which is the exact value that I want. So again, t equals 4 is our key. Right? So now we have the t value that corresponds to this point. So now we can plug that t value into the first derivative and into the second derivative, and that will give us our slope and concavity at that point. All right? So our slope at the point 2, 3, which is the same, oops, scoot this over a little bit. I'm going to put, in other words, at t equals 4 is dy over dx. I'm going to plug in t equals 4 in there. So I want 4, because t equals 4, to the 3/2, which is, the square root of 4 is 2, so 2 cubed, which is 8. Right? So my slope is 8 at that point. And my concavity at the point 2, 3, again, which is the same as the point at t equals 4, is d squared y over dx squared, which is 3 times t, which is 4, so 12. Remember, for concavity, all we need to know is that it's greater than or less than or equal to 0, right? So I know here, since it's greater than 0, it's concave up, or it looks like a smiley face, right? And then looking at the graph here, this graph here is just to prove what we already know, right? Here's our point t at t equals 4, which is the point 2, 3. We know that has a really steep slope, right? This has a slope of 8, right? And as you can see there, it's a very, very steep slope, and it's concave up, right? It looks like a smiley face at that point, right? So we are just verifying the results that we got. So a little bit of a note here, because the parametric equations x equals f of t and y equals g of t need not be defined y as a function of x. That means it's possible for a plane curve to loop around and cross itself, right? So in general, when we were talking about and y as a function of x, it had to pass the vertical line test, right, in order for it to be a function. Now, since we have these parametric equations that don't have that stipulation, we can have curves that cross themselves. And therefore, we can have curves that have more than one tangent, right? So this is an example here. I already did the graph, but let's do the work to find all this information, right? So this is called a prolate cycloid. It's given by these parametric equations, y equals 2t minus pi sine t, and y equals 2 minus pi cosine t, and it crosses itself at the point 0, 2, and so it has two tangent lines there. Okay, so the question is to find the equation of both tangent lines at this point. And in order to find the equation of a tangent line, what do we need? In order to find the equation of a line, we need a point and a slope, right? So we need a point and a slope here, we should figure out our derivative function so that way we can, because remember the equation of a tangent line, how do we get the slope of a tangent line? We get it from the derivative, right? So let's find our derivative. So dx dt is going to be the derivative of 2t, which is t, and then minus pi cosine of t. dy dt is equal to the derivative of 2 is 0, the derivative of negative cosine is positive sine, so I get pi sine of t. So dy over dx, by definition, is dy dt over dx dt, which is dy is pi sine of t over top of 2 minus pi cosine of t. All right, so that's our equation for our derivative. And we want the derivative at the point at the point 0, 2. So we need to find the t value, once again, that corresponds to the point t equals 2. But notice that since our graph crosses itself, that means at two different t values, it will give us that point, right? So in other words, we need to find the two t values that give us the point 0, 2, right? So in order to do that, I guess I don't need to mark it. I have my x equation, which is 2t minus pi sine of t. I know that at these two t values that I want to find, that's equal to the x value here, which is 0. And I know that the y value is given by 2 minus pi cosine of t, and I know that I want to find the t value where that equals to 2. So if you notice, this y equation is actually pretty complicated, or I'm sorry, this x equation is complicated. Why is it more complicated? Well, it has a t in both terms, right? It has a 2t and a sine of t. So it's actually going to be easier to look at the y equation because it'll be easier to solve, right? And in this case, I could look at either one because either one is going to give me the same two t values, right? So here, if I subtracted 2, I would get 0 on the other side, and then if I add cosine, so this ends up getting 0 is equal to pi cosine of t. Divide by pi, I end up getting 0 is equal to cosine of t. And when is cosine equal to 0? That happens at t equals pi over 2 and t equals negative pi over 2. All right? I could have picked 3 pi over 2, but if you look at this, if we look at our equations here, notice that these slopes, or these have exactly opposite slopes. And so our equation will actually end up looking better if I have t equals pi over 2 and t equals negative pi over 2. Actually, it'll give, I'm sorry, I don't know why I'm even saying that. It'll give us the same answer. I could have put 3 pi, or I could have put 3 pi over 2 here. Because 3 pi over 2 also gives me the same values. And remember, what am I going to do with this t value? I'm going to plug it into there, right? So I could have picked 3 pi over 2 there. Wouldn't have mattered. But those are my two t values, right? So now I want to know, those are my two t values where I'm looking for tangents, right? So in order to find the equation of the tangent lines, I need to find the slope of the tangent lines. So to find the slope of the tangent lines, I guess I don't even need to write that. Let's just say this. At t equals pi over 2, my slope dy over dx is equal to pi sine of pi over 2 over top of 2 minus pi cosine at pi over 2. Right? And this is going to give us, calculating this will give us what our slope is at that point. So sine at pi over 2 is 1, right? So I just get pi, and then cosine at pi over 2 is 0, so I get 2, right? And at this point, what's my y-intercept of my graph? At that point, it actually is a y-intercept because it's just on the graph, right? So my y-intercept is 2. So my equation of my line is y equals pi over 2x, because pi over 2 is my slope. Sorry, I get a little glitch in my thing here every once in a while. Wow, okay. This is my slope, right? And then plus the y-intercept of the line, but again, the line crosses the y-axis at 2, so my y-intercept is 2. And then at t equals negative pi over 2, my slope dy over dx is equal to pi sine at negative pi over 2, 2 minus pi cosine at negative pi over 2. Sine at negative pi over 2 is negative 1, so I get negative pi. And then cosine at negative pi over 2 is 0. So that's my slope there. So now this line is y equals negative pi over 2x plus that same y-intercept 2. So those are going to be the equations of a line. And as you can see there, this is a line with slope pi over 2, and this is a line with slope pi over 2. And so that is our equation of our tangent lines. All right, so I'm going to go ahead and end this video here, and we'll pick up in the next video with example 4.